in an equilibrium situation, you're either given starting conditions with a little bit of information about the equilibrium and solving for the equilibrium constant, or using the equilibrium constant and a bunch of concentrations to figure out missing information. But one of the common tricks is starting with some known amounts and predicting how much material you can make at equilibrium. And this is where equilibrium are really powerful. It's the predictive capabilities of figuring out what's the concentration of everything at equilibrium. And the reason we can get there is because the equilibrium constant is a constant, and the concentrations are not independent of one another. We can use stoichiometry to tell us. So this is where our ice table comes in. Again, just like in our D4 examples, the ice table, we fill in as much as we can, and then we can try and solve for equilibrium concentration. So let's take a look at this example. This is the one I did in class. 0.1 molar solution of H2, 0.2 molar of I2 makes some HI, and we want to know how much. All right, what is the concentration of HI at equilibrium? If we can set it up and solve for the change, we are often capable of solving for these concentrations. So our initial concentrations, no surprise, 0.100 molar, 0.200 molar, and 0 molar. Some of this is going to be lost to make HI, and so we'll just call that minus X. And for every one of those that's lost, we gain one of those. And for every one of those that's lost, it's also going to consume an equal amount of the iodine. And that will produce 2 HI. Again, not unexpected from our ice table. So at equilibrium, we can combine these two. At equilibrium, the H2 will be whatever's lost, 0.100 molar minus what's lost, what's left. So at equilibrium, the H2 is going to be whatever's left over, 0.100 minus X, and 0.200 minus X. And at equilibrium, this will be whatever had been consumed. And we're left with potential concentrations at equilibrium. Now that alone isn't very useful, but it's not alone. We know that our equilibrium is a constant. 19 will equal the amount of HI squared over the amount of H2 and the amount of I2. Well, we have those values, and so we can plug them into our equilibrium statement. Once we do this, you get a form that looks like this, where 19 is equal to 2x divided by 0.1 molar minus x, 0.2 molar minus x. Now all we have to do is a little bit of algebra magic, and out comes an answer. If we can rearrange this and solve for x, we're good. And so that's exactly what I'm going to do. And we get this long form, which we can combine the variables into x squared plus minus 0.300x plus 0.02. So that is now our denominator. So that is now our denominator in this system. And we can multiply it across, multiply by 19, and so we get 19x squared minus So we multiply this entire thing by 19 to give us our left-hand side of the equation. And this simplifies then to equals 2x squared, which is equal to 4x squared. And then we can combine these to 19x squared minus 5.7x plus 0.38. If we were lucky, there would only be one x, but we have multiple x's, and so they're difficult to combine, and so we have to rely on the quadratic equation or some other simplification. And so to get it in the quadratic equation, what we care about is it in the form of ax squared plus bx plus c equals 0. So we have to make one side of this equation equal to 0. And so in this case, we'd subtract both sides, negative 4x from both sides. So this becomes 15x squared minus 5.7x plus 0.38 is equal to 0x is equal to 0, which is in the correct form, ax squared bx c, and then we can solve using the quadratic formula. Quadratic formula is provided. I'm not going to show you how to use it. You guys all had algebra, but we'll plug in our values and we'll get 2x values. I cheat. I use a quadratic formula solver. So you use whatever math technique that you like, and you should get out two values for x. X is equal to 0.293, and x is equal to 0.0862. So these two numbers by themselves, again, not overly useful, but we built this ICE table, and in the ICE table we had the concentration of H2 is equal to 0.1 molar minus x. You can plug in these two x's and you would get a value. The problem is only one of those values is sensical. So if we use this first x, this number 0.1 molar minus 0.293 will be a negative concentration. Not useful. But it allows us to then recognize that the second number is useful. And so if that's the case, if x then becomes valid, then we know that H2 concentration will equal 0.100 molar minus 0.0862 molar equals 1. So at equilibrium, this will be point. At equilibrium, this will be 0.0138. I2 will be a little bit higher. 0.11. And so at equilibrium, we get equilibrium concentration of HI equal to about 0.174 molar. Now is the important part. Do the answers make sense? The only way to tell is just to check. Right? We know K should be equal to 19, so if we plug these values into their appropriate spots on the equilibrium expression, hi squared divided by h2 divided by I2. They should equal 19. So let's test it. 0.1724 squared divided by 0.1138 and 0.0138. And I get a tentative K of 18.9, which is within rounding errors 19 for our answer. So the check works. It's a long drawn out procedure, but if you can get it into a quadratic form, you can numerically solve it. But there are simplifications.